All right, so we're in section 14.4.
Oh, that's why. It's like a lukewarm water. You really want it there?
All right, so last semester we worked a little bit with finding the mass and the center of mass of planar lamina, so thin slab of something that's in a plane, and we assumed that it had that these planar lamina had constant density. That made our calculations easy. And we said our assumption was that rho was a constant mass per unit area. And we said what our assumption was last semester was if rho is constant, so we have a constant density, the mass of a planar lamina of an area in the plane is just rho times the area. So with what we've been working on, we would say that the mass m is just going to be rho times the area of whatever our region is, and we've been finding our area with a double integral, so that would just be a rho integral over our region dA. So we're just multiplying our constant density times the area of our region. Well, now that we have this tool of double integration, we can work with a variable density. So if rho is variable, so our density depends on where we're located. We're going to say it's a function of x and y. Our mass is going to be the double integral over our region of rho xy dA. So we can find the mass of a region when we have variable density. And what we're saying here is that, just a quick sketch, if we're in rectangular coordinates, our little increment of mass is here, and we're located at y sub I, and we're located at x sub I, and we're just summing all of these. So the mass of this little piece is our density at that area times delta A sub I. And we're just summing these little pieces of mass over whatever our region is. So this is so we have a way of finding, if we know this density function, we can find the mass of a region. We just do our regular double integral, and we can find the mass of a region. So just exactly the same as what we've been doing, just kind of a different application. Now what we're going to do is use this idea of this density function and looking at a mass of a little section of our region, and use that to find our center of mass and our moments. And I'm just going to abbreviate center of mass, COM. And when we worked with center of mass last semester, we defined the center of mass, or we defined the moment about the x and y axis for a lamina of uniform density as the mass times its distance from that axis. So the moment about the x-axis was the mass times its distance from the x-axis. The moment about the y-axis was its mass times its distance from the y-axis. And we used some methods to simplify our calculations when we were talking about center of mass. We assumed that our density was uniform. We assumed that the mass was concentrated at the center of our little region, and that's how we ended up calculating center of mass. If we have a variable mass density, we can use double integrals, and we don't have to make those simplifying assumptions. So what we're going to do is, just like our little drawing for our mass, we're going to look at a little piece of a region, so we have some region in the plane. And we have a little increment, a little piece of mass here. And just like before, this is our mass, is our density times our area. And I'll say delta A sub I. And this little piece of mass is located, the center is at y sub I, x sub I. And our moment about the x-axis, we're going to say that m sub I times y sub I is going to be our density at that particular location. Times its distance from the x-axis, which is just y sub I. And our moment about the y-axis is our density function at that particular location times our area. And we add these all together, we sum these over the region to get our total moment. And we take the limit just like we've done before. It's the same argument that we've used when we set up our double integrals, so I'm not going to go through the whole thing again. But we take the limit as delta A approaches 0, the same kind of idea, and we sum that over the entire region. We end up with a double integral. So motivated by this, we're going to define, and it's referred to in several different ways. So we're going to define the moment you'll hear it referred to as moment of mass. Or the first moment of mass. And we're going to talk about our two different axes. So our moment of mass, first moment of mass, all of those refer to the same thing. Moment just means we're weighting something by its distance from the axis. We could talk about all different kinds of moments, but right now we're talking about moments of mass. So with respect to the x-axis, and we call it m sub x just like before, is going to be our double integral over a region of y times our variable density function dA. And with respect to the y-axis, m sub y is just the double integral over our region of x times our variable density function dA. So this is our definition of our moment of mass, first moment of mass, with respect to our two axes. So we don't have to make those simplifying assumptions. We don't have to assume that it's at the center of a little rectangle. We can just multiply our little increment of mass times its distance from the axis and take the double integral over our region. And then the center of mass of our region, and we'll use the abbreviation COM again, is, and we say X bar, Y bar for our center of mass, is m sub y divided by the mass of the region for our x coordinate, and m sub x divided by the mass of the region for the y coordinate, where m is our double integral over our region of rho x y dA. So that's how we find the coordinates of the center of mass. So now we can find the center of mass of some region with a variable mass density. And remember, when we talked about these last semester, we talked about the centroid. The centroid, and I mentioned this briefly, the centroid usually refers to a lamina with a uniform density. So centroid then is a property of the shape, not the material. So because we're talking about a variable mass density, we're going to talk about the center of mass, because the location of the center of mass depends on the shape and the material. And the centroid is just a property of, usually just a property of the shape. So questions about our definitions. So these just give us some other tools, some other ways that we can apply double integrals. So what I want to do is look at one example of finding a moment in the center of mass, and then we're going to talk about a second moment and what a second moment tells us. All right, so let's look at a calculation. So we want to find the mass in the center of mass. And our region is bounded by y equals x to the third, y equals 0, x equals 2, and our mass density is some constant times x. So as we move further along the x-axis, our mass density increases. So what's going to be the first thing? What do we want to do first here to find our mass, center of mass? Let's draw our region. So make a quick sketch of our region. So y equals x to the third. It's going to go something like this. And x equals 2, like so. And y equals 0 down here at the x-axis. So our region is there. So we want to set up our double integral. So what's going to be the best way? How do we want to set up our double integral here? How do we want to set it up? Want to set a vertical rectangle? That would be my choice. So our mass. Find our mass first. So our mass is just going to be the integral of our density, k times x, and our vertical rectangle we're going to do dy dx. So our inner limits of integration, our y limits of integration, y varies from what to what? 0 to x cubed, and x is going to vary from 0 to 2. So we evaluate this this integral. We'll evaluate the inner integral. So we get 0 to 2. We're integrating with respect to y. So we get kx y. Evaluated on 0 to x to the third, and we still have our dx out here. And we end up with, I'm going to put my k, integral from 0 to 2 of x to the fourth dx. And we finally evaluate that, 0 to x to the fifth over 5, evaluated on 0 to 2. And our mass comes out to be 32k over 5. So a nice easy evaluation. Now we're going to set up our integrals for, now the bad thing about moments, mass, center of mass, you end up doing a lot of integrals. So let's set up our m sub x, our moment about the x-axis. So we're going to have our same limits of integration, same set up our vertical rectangles. So everything's going to be the same, it's just we have a slightly different integrand. So the moment about the x, we're just going to put a y into this integral. So we get k yx dy dx. Not difficult to evaluate. I'm not going to go through the evaluation. This is not a difficult integral to evaluate. We end up with, when we evaluate this out, 16k. K is just some constant. And our moment about the y, same limits. Everything's the same except we have an additional x in there. So we get kx squared dy dx. And when we evaluate that, we end up with 32k over 3. So we end up with all three of these integrals to evaluate, and then our center of mass, x bar, is going to be, again, our m sub y over m, and we end up with 32k over 3 times 5 over 32k, and we get 5/3. And our y bar, m sub x over m, 16k times 5 over 32k, and we get 5/2. And on these, I suggest that when you come up with your coordinates of your center of mass, you go back and double check. Does 5/3 and 5/2 make sense here? We would guess that the center of mass, because the mass gets larger as x gets bigger, it's going to be further over this way, so it's going to be somewhere over here, and our coordinates seem to make sense. Questions on that example? All right. So let's talk about another moment. So our m sub x and m sub y are moments, are our first moments of mass. We call them the first moment because we're weighting them by its distance from the x-axis. Our distance, we call it the first moment because our distance is raised to the first power. So we can define our second moment of mass, or moment of inertia, is its mass times the distance squared. So we call it the second moment because our distance is the second power. And our distance, we mean a distance from some axis. So we call this the second moment of mass. And the moment of inertia is a measure of the tendency of mass to resist change in rotation. So we're going to follow the same kind of reasoning that we talked about. We could draw our little region. Our region is the same. We have a little piece of mass, and we're just multiplying that mass times the square of its distance from a particular axis. So it's the same argument. We're just using distance squared rather than distance for our second moment of mass, or a moment of inertia. So we're going to define I sub x, the moment of inertia about the x-axis, is a double integral over our region of y squared times our density function dy dx, or I should say dA. dy dx if we're in rectangular coordinates. And I sub y, the moment of inertia about the y-axis, x squared times our density times our piece of area. So we call this the second moment of mass, or moment of inertia about the x-axis. And this one is about the y-axis. And if we sum these two, I sub x plus I sub y, we call that the moment of inertia about the origin, or about the z-axis, or the polar moment of inertia. And that's just going to be the double integral of x squared plus y squared times our density function times our area. Or we could write that as r squared times our density times our area. So this is the polar moment of inertia. Or the second moment about the z-axis. Or we could also talk about it being the moment about the origin. And usually if a problem asks you to find the polar moment of inertia or the moment about the z-axis, it's usually easier to calculate these separately. I find it easier to calculate them separately than to try to put them together. But if you're, and we'll talk, when we get further, we'll talk about cylindrical coordinates. Sometimes in cylindrical coordinates, this integral turns out pretty nice. And we could talk about third moments and fourth moments and fifth moments, and they're used in various different kinds of applications. There's actually, in statistics, there's a third moment that's used. It's how the data distribution is weighted. The third power is distance from the mean or something like that. You could ask Mr. Grace about that. He'd probably really like it if you did that. So we're just defining these different moments and using double integrals to evaluate them. So any questions on our definitions? All right, one other little piece of information that I need to talk about for this section, and then maybe we'll look at one more example. So second, we have the first moment of mass, second moment of mass. The last little piece of information is the radius of gyration. the radius of a gyration. The symbol is R double bar. So radius of gyration R, and we're talking about a revolving mass. And our moment of inertia is I. And so our double bar is the square root of I over m. And what the radius of gyration tells us is if the entire mass were concentrated at a distance, R double bar, from the axis of revolution, it would have the same moment of inertia as the entire system rotating about the same axis. So the radius of gyration, if in physics, it can be used to simplify your work. It tells us, it allows us to assume that the entire mass is that distance from our axis, and the moment of inertia is the same. So our radius of gyration is given by the square root of the moment of inertia divided by the mass. So if it asks for the coordinates of the radius of gyration, we would say that the x coordinate is just I sub x. Sorry, I sub y over m, and the y coordinate is I sub x over m. So really finding the radius of gyration is not any different than finding the moment of inertia in the mass. Same process, we just have this additional calculation to do. And there are a couple of problems that ask you about the radius of gyration in your homework. All right, questions? Questions on what we've talked about?
Just one.
Yes.
So the radius of gyration, does it give you a point when you calculate that out, or do you expect like a value? Like for the I over m, would you expect a point like x equal to y?
Yeah. So that would be the coordinate. That would be the coordinates of the point that you could assume that the mass was concentrated at, and it would have the same moment of inertia as the entire system rotating about that axis.
Right.
Okay. All right. So let me pick out a good example here, and we'll do one example. And then we will be done. Okay, so let's do one example, and then we'll stop. So we want to find, for this example, we want to find I sub x, our moment of inertia about the x-axis, I sub y, I sub o, x double bar, and y double bar. And our region is bounded by y equals x squared, y squared equals x, and our density function is x squared plus y squared. So we want to sketch our region. First thing to do is going to be sketch our region. So there's y equals x squared, and here's x equals y squared. So our region is in here. And where do these two intersect? What's this point going to be? 1, 1. So what I want to do here, we're not going to evaluate these integrals, we just want to set them up. So, and what I'll do, there are questions when we do these kinds of questions on a quiz or a test, kind of like when we did moments of inertia, when we did moments before. I'll ask you to set up but not evaluate the integrals, because there's a lot of evaluation involved. So we need to find our moments, our second moments about each axis, our polar moment, and our radius of gyration. So we need to find m, our mass. We need to find the moment about the x and the moment about the y. So let's set up our integral for m. How do we want to set up our integrals here? We know we have our density in there. So choose vertical rectangles. So y is going to vary from x squared to square root of x. And x is going to vary from 0 to 1. So that would be our integral that we would evaluate for the mass. Our moment about the x-axis, I sub x, 0 to 1, x squared to square root of x. Our density function, yeah, Eric.
Just say one of your equations is y squared equals x squared, but you mean y squared equals x.
Oh yes. I was moving ahead to this one. Thank you. So there's our moment about the x, and our moment about the x is we include a y squared in that integral. And these integrals, these particular ones are not going to be hard to evaluate. We just have polynomials. I sub y are same limits, 0 to 1, x squared, square root of x, and then we have square of our distance from the y-axis times our density function. And then our moment, or our radius of gyration, our polar moment, is just going to be the sum of these two. And a radius of gyration, x double bar, is just I sub y over m, and y double bar is I sub x over m. So these integrals, these three integrals are our key integrals for all of these. We set them up, not going to evaluate. So any questions? Nothing particularly new, just kind of a different application, a different thing to do with double integrals. All right.